and if there's a warning, you fix it. Another example, very briefly, is shown here. That is, let's say you have a definition, what here called list entry. The definition is then being used, and as part of this macro that's being applied here, you have a cast, where an element is being cast to some other pointer type. The issue with this is that this element here is not type checked. If you have any pointer type, this cast will work, even if it's not the right type. It should be a type to a list element, or that type up here, but this macro doesn't enforce it. So in this case, what we've done, we've changed the macro to use this down here, and as a result, when students made the mistake of passing a list element pointer that was not that type, we get a compiler warning, because the type that is expected here must have a field next. If it doesn't have a field next, this will not compile, and then such a wrong use of the list entry macro would fail during the compile phase. So if the compiler warnings, if you don't get compiler warnings, change your code to help the compiler give you warnings if you make wrong uses. Okay, so don't start debugging until the program compiles, highest warning level. At this point, what you're optimizing for is not performance, it is readability, and it is understandability. And sometimes you hear people make the argument that they say, oh, this is a warning. I say, well, the warning is benign. Okay, so first of all, in many cases, warning is not benign, or you don't understand whether it is or not. And in all cases, the burden of proof is on you. If you change the code so that the warning disappears, is the code in fact easier to read or not easier to read? And it's oftentimes, if you to ignore a warning, you have to make the case that the code with the warning ignored is easier to read than otherwise. That's often a hard case to make. All right. A note on compiler optimizations. For the tools that I'm going to be talking about next, GDB, Valgrind, and so on, those tools work on compiled executables. And when you compile an executable, you load the compiler. By the way, I assume that everybody here has some familiarity with C or C++, building programs like that. C++ programs. So when you use the compiler, you specify the -o switch to turn on optimizations. By default, if you say -o, if you don't say -o, I'm sorry, that means optimizations are off. By convention, that means that the compiler produces code that is entirely unoptimized. It is extremely naive code. It's kind of the code that a student compiler will produce in an introductory class to compilers. Okay? There's no register allocations, variables are not kept in registers, reloaded from memory, operated on, written back to memory, extremely slow code. But that code is also is the closest you can get to the actual source code. And that helps many of the debugging tools, okay? Because as you do dynamic analysis on the executable, you find any faults or anything that is noteworthy, you need to relate back to the source code, and not compiling with optimization accomplishes that. And I want to point out, even if you just say -o, which is equivalent to -o1, you're giving the compiler permission to perform some optimizations, so there's inlining that may prevent you from using certain tools. And also on the x86, you do not want to use the FOMID frame pointer option in order to ensure that you get correct back traces. This is a comment that applies to all the following tools, and oftentimes when you're debugging something and it looks like the debugging info is weird or so, double check that you didn't compile with optimizations.